In today's lesson, we're going to be discussing the number of outcomes that are possible in an event without actually having to draw out our sample space every time, because drawing out our sample space can get really large. So many times numbers get large really quickly. For example here, if I wanted to know how many outfits I can create with 3 shirts, 2 pants, and 4 hats, I could have drawn out a sample space and said picking out my shirt gives me 3 options. Picking out my pants gives me 2 options for every one of those 3, and picking out my hat gives me 4 options for every one of those 6 options. Well, where did the 6 come from? Well, I started off with 3, and I have 2 options per shirt, so that gives me 6 outfits with my shirt and pants. I have 6 different outcomes there. Therefore, if I have 4 choices for a hat, I have 4 choices for each of those 6 outfits. So altogether I have 3 times 2 times 4, which is 24 outfits can be made. So I now know there are 24 outfits that can be made. So if I want to know what's the probability of shirt 1, pant 1, hat 1, then I can say, oh, 1 out of 24, right? So how did I get to this 24? Well, I found out there were 3 options for my first event, picking a shirt. There were 2 options for my second event, picking a pair of pants. And there were 4 options for my third event, picking a hat. So if you multiply the number of possibilities per event, you get the total number of outcomes. This is called the fundamental counting theorem, if you do that. So for example, if I have a game and I have 4 options in the first spin and I have 3 options in the second spin, altogether I have 4 multiplied by 3, I have 12 different possibilities or outcomes. I could go 3-3, I could go 3-2, I could go 4-1, I could keep going, but I know that the total number of different possibilities, combinations that I can put together is 12. Dan can take 4 different classes first period, 3 in the second, and 5 different classes third. How many different schedules can he have? Well, there's 4 possibilities in choosing the first class. There are 3 possibilities in the second, and 5 possibilities in the third. So altogether we have 4 times 3 times 6, 4 times 3 times 5, which is 60 different schedules. So that is our fundamental counting theorem that we can use to calculate the number of outcomes. We use these number of outcomes to then be able to determine probabilities, because the number of outcomes is our sample space, or our denominator in our probability questions. So in general, the total number of possible outcomes can be determined by multiplying the number of possible outcomes for each event. This is our fundamental counting theorem. So let's try this one. Determine the number of possible outcomes when rolling a 4-sided die 3 times in a row. Well, the number of outcomes, 1, 2, 3, or 4, multiplied by the number of outcomes, 1, 2, 3, or 4, multiplied, hey, it's just 4 times 4 times 4, which is, in other words, I could always write as 4 to the power of 3, and 4 to the power of 3 is 64. There are 64 different possibilities. At Baskin-Robbins, you can go in and there are 31 flavors of ice cream. So it's so difficult to choose. How many triple scoop ice cream cones can be made? So if the first scoop of your ice cream cone, you can choose any of the 31 flavors, you would get 31. And then the second one, you can choose any of the 31. You can repeat a flavor. For example, if you really like vanilla, you can have vanilla, 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 right? You can choose vanilla 3 times if you wanted to, so you still have 31 flavors to choose from. And in the third one, again, you have 31 flavors. Now, 31 times 31 times 31, or in other words, 31 to the power of 3 gets really large. You have a total of 29,791 different outcomes. Now, be careful here, because if you really like strawberry and vanilla and you like strawberry a little bit better, you could go strawberry, vanilla, strawberry. You could go strawberry, strawberry, vanilla, right? You could go vanilla, strawberry, strawberry. Those are all considered different options, right? Those are all considered different options. It doesn't mean like only having one strawberry or one vanilla and two strawberries is one of those options. The order matters, right? So you're coming up with a number of outcomes, but different orders are considered a different outcome. Okay, so it gets quite complicated, and you'll take this up later in later years. But for now, just know that by multiplying the number of outcomes in each step, you get the total number of outcomes. But order matters, right? So that if you wanted to find out how many of these combinations have two strawberries and a vanilla, you'd have to order them all out and figure it out. How many of those have that? And then you could figure out how many have two strawberries and one vanilla, right? And you could use that to change the number of, or to determine that. How many 4-digit combinations are possible using the digits 0 through 9? So I want to make a 4-digit combination for my locker, and I have 0 through 9, right? So if you have digits 0 through 9, how many options are there for the first digit? Well, you could have 0, 1, 2, 3, 4, all the way through 9. That gives you 10. Those are 10 different digits, right? So you have 10 options for the first. And again, it doesn't say you can't repeat. 0, 0, 0, 0 could be your combination. 10, 10, and 10. Or in other words, 10 to the power of 4, which becomes 10,000 options. Okay? So just using those 10 digits and making a 4-digit number, you have 10,000 different locks you can make that are all unique to each other. And again, a reminder, a 0100 is unique to 0010, right? Order matters. Those are different combinations. How many 4-digit numbers are there? Okay, so this is a little bit different. It's not quite 9,000 because in a number, you would never start the first digit with 0. The first digit has to be a 1, a 2, all the way through 9, right? So you actually only have 9 options for the first number. You can't use a 0. And then the second digit, well, it can be a 0, so you now have 10 options in the second digit. And you can repeat, and you can use a 0 again, so you have 10 options for the third digit. And again, you can repeat and use 0 again, so you have 10 options for the third. So how many numbers are there that are 4-digit numbers? 9 times 10 times 10 times 10 is there's 9,000 numbers. So this fundamental counting theorem is a really handy way to be able to calculate how many numbers there are as a 4-digit, 3-digit, etc. How many 4-digit numbers are divisible by 5? Well, it's the same type of question, but we have to tweak it a bit. Again, you only have 9 options for the first, 1 through 9. The middle 2 digits can be anything, 0 all the way through 9. But since it's divisible by 5, we know it ends in a 0 or a 5. There's only 2 options for that last digit, right? It has to end in a 0 or it has to end in a 5. So now we multiply those all together and we get, oh, there's now 4,500. Is that right? 9 times 10 times 10 times 2. Sorry, it didn't sound right. There are now 1,800, which makes sense. 9 times 2 is 18. 1,800 numbers. All right, let's try another one. How many 7-digit phone numbers are available if the first digit must be a 5 or 7? Well, the first digit must be a 5 or 7, so there's only 2 options for the first digit. But for each of the other options, so second, third, fourth, fifth, sixth, seventh, we can use any number. We can use 0 through 9. So there's 10 options for each of those. So in other words, when we multiply this, we're going to get a 2 with 6 zeros, or 2 million options. So this tells you how many numbers can be made. How many ways is there to arrange the letters A, B, C, D, and E? This is where things change up a bit. All right? When we're only given a select numbers, And if we want to arrange them, for example, if I put B first, I've used up the B. The B's gone. So I don't have 5 options. I now only have an A, C, D, or E. Let's pretend I use the A. The A's gone. Now I only have a C, D, or E. There's only 3 choices. If I use the C, I only have 2 choices, right? If I use the D, I only have 1 choice. So how can I figure out how many choices, how many ways we can rearrange it when every time I use something, one of them disappears, one of my options disappears? Well, I would do the exact same thing as I did before, but I would just reduce the number of possibilities or outcomes for each. So how many different things can go in the first place? Well, it could be an A, a B, a C, a D, or an E. So there's 5 options for the first letter. Once I've used one of those options, I can't cross it off because I don't know which one it is, but I'm left with 4 for the second. Now I have 2 numbers I've used, so now I have 3, then I have 2, and then I have 1. So I just multiply 5, 4, 3, 2, or 1, and I get 5 times 4 times 3 times 2 times 1 gives me 120. So there are 120 different ways I can order those 5 letters. Now, look at this. 5. If I wanted to order 6 letters, what would be the difference? I would have started with 6 and gone down to 5, down to 4, down to 3, ... If I had another letter, 7, it would be 7, 6, 5, 4, 3, 2, 1. So you can see the pattern here. So in math, what they have done is they've come up with a notation rather than always writing all the way down, starting at 7, going down to 1, because what if there were 100 letters? You'd be like 100 times 99 times 98, you'd be writing forever, right? So another way to write 5 times 4 times 3 times 2 times 1 is 5, and you put this exclamation mark. That means factorial. 5 factorial means you take the 5 and you keep taking 1 off, all the integers below it down to 1, and that's 5 factorial is the number of outcomes to arrange 5 things. 7 factorial is the number of outcomes to arrange 7 things, right? So that is a new notation that is used in probability and mathematics, factorial. How many ways are there for 8 people to finish first, second, and third? So there's 8 different people. We'll call them person A, B, C, D, E, F, G, H. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. That is. So how many options do we have to finish first? Well, we have 8 different people. A could finish first, B, etc. So let's pretend D finished first. So there's 8 options. But let's pretend it was D. Now how many options do we have? Oh, we have 7 options, right? So let's pretend it's E who finished next, but there were 7 different people who could have finished next. And so E is gone. Now we have 1, 2, 3, 4, 5, 6 options, right? And it could be any one of those 6. I don't know, like B, for example. Oh, D, E, B, D. That is one order of finishing first, second, and third. Again, order matters. That will be considered a different outcome than B, E, D. That's a different outcome. Person B, then E, then D is different than this one. So order matters, right? We actually call that a permutation. The way you can, how many ways you can arrange things in which order matters. So there are basically, let's get rid of the D, E, B because that was just an example. There were 8 choices for the first, and we had 7, and then we had 6. We don't go all the way down to the 5, 4, 3, 2, 1 because we're only picking 3 out of the 8. Okay? And some people even, you can use notation. Picking 3 out of the 8 for a permutation. We're not going to get into all to the fancy stuff. You just have to do it this way. 8 times 7 times 6 is 336 ways that we can finish first, second, and third. 3 people out of 8. Same thing with our ice cream. Remember before we had 31 flavors, okay? But what if all the flavors had to be different? So you couldn't, if you chose vanilla for your first scoop, you can't choose vanilla for your second, etc. Okay, so you would have 31 flavors, then you would have 30, and then you would have 29, and then you would multiply that together to find out the total number of flavors that all flavors are different. But again, order matters. So if you like vanilla, chocolate, and strawberry, right, that's a different outcome than strawberry, vanilla, chocolate. Order matters. So there's different ways in which you could have gotten 3 flavors that are all different. Okay, so let's just type this in. 31 times 30 times 29. Whoops. And I get 26,970 different possible outcomes. There are 9 players on a baseball team. How many ways can a coach pick the first 4? Well, he has 9 people to pick from, then 8, then 7, then 6, right? So I think we're getting the idea of how to use our number of options in each event to calculate the total number of outcomes. Now let's get into a couple tricky ones. I think we did this. Oh yeah, we can do the same question again, but this time all of the digits have to be different. I'm just going to skip that one. I'll put that in our notes. Let's get into some trickier ones. How many ways can we arrange A, B, C, D, and E, but A, B has to sit beside each other? So it doesn't matter which order you do it, A, B has to be beside each other, right? So they come as a pair. You can't split them up. So what I do with this is if A, B has to be beside each other, I treat A, B as one thing. I just treat them together. A, B is an option, C is an option, D is an option, E is an option. So even though there's 5 letters, I really in my first blank only have one choice. It could be A, B, it could be C, it could be D, or it could be E. So by treating it as one, I can now say, oh, I have 4 choices, then I have 3 choices, then I have 2 choices, then I have 1 choice, or 4 factorial, which gives me 24 ways they can sit beside each other. But each one of these is where A is first and B is second, right? So all of those 24 options have A first, B second. AB could have been here, or AB could have been last, or AB could have been in the middle, but in all of those options, it went A first, then B. So don't forget that AB has 2 ways to order it. It could be BA or AB. So since I have 24 ways with A then B, I just have to double that, right? Because you also have BA as an option, so each one of those options also has BA as the option, so it's actually 48 different ways. Okay. What if I did the same question, but I said A, B, C has to go together? They have to sit beside each other, right? Going to the movie theater, you've got 6 seats. A, B, and C have to be together. It doesn't matter if it's A, B, C or C, A, B, right? Or B, A, C. I think I might have said that, I can't remember, but anyway, A, B, and C have to be beside each other. Again, you treat them as one, right? So that's an option, D is an option, E. So it's the same thing. You have 4 options for the first, 3 options for the second, 2, and then 1, right? Which is 24 different ways. But now you have to think about how many ways can you order A, B, C? Well, this time it's not just 2. You can order A, B, C by saying, well, A, there's 3 options to sit first. There's 2 options in the second seat, and then 1 or 3 factorial ways to order A, B, C, which is 6 ways, right? If we listed them all out, you would know that you would see that there's 6 ways to order A, B, and C. So since there's 6 ways to order A, B, and C, I now multiply this 24 because this one, A, B, and C, has 6 different ways. So each one of these options has 6 different ways. So you go 24 by 6 and you get 144 ways to order those 6 numbers in which A, B, and C must be beside each other. That's a little bit tricky, little hint there. And here's our last question of the day. It's a double star because it's even more difficult. How many ways are there for 3 people to finish first, second, and third out of 5? Right? So we've already done a question like that, but I'm going to add something in. Person A has to be one of the top 3. Okay? So if person A has to be one of the top 3, we have 3 cases. Case 1. A is first. Right? If it has to be the top 3, let's say A is first. So if A is first, there's no options for first place. How many options do we have for second place? Well, if there are 5 people, we have 4 options because A is already taken. And then we have 3 options. There's only 1 option because we chose A to be first. So if A is first, there's 12 different ways that can happen. Case 2, what if A is second? Right? A has to be in second place. Again, there's 4 options here, 3 options here, only 1 option here because we've already chosen A. So there's 12 different things. So these are our different options. Or case 3, what if A is third, right? So if A is third, again, there's 4 options for first, 3 options, and so A is just 1 option, which is 12. So since we have or, this could happen, or this could happen, or this could happen, all together we have 12 options plus 12 options plus 12 options. So sometimes I can make it tricky and you have to say, okay, well, if A has to be in the top 3, you have to make it a case scenario. You have to figure out, okay, well, if A is first, how many options? If A is second, etc. So all together we have 36 outcomes. That's a tricky one. All right, so you can work on your fundamental counting or your number of outcomes worksheet. And there's some tricky ones in there, so if you're struggling, just ask for help and I can give you some hints.